Good evening, ladies and gentlemen. This is Econia, and I'm gonna show you what I wasted my last days on, or with whatever English grammar. Who needs it? Not me. This is a freestyle video, as you may have mentioned. I have not planned anything. I'm just gonna show you the result at first, which is what you can see here. This is a big bad ROM. It's 8 bits in 2 blocks wide per bit, and it has 256 addresses. Yeah, it's super tasty. You can see how the current address, the current active address goes here. Walks to the end of it. And if a wire is set here, the current bit will be sent to the output. If not, that's a 0 bit. And it's pretty compact in my opinion. It's not as small as the one auto ROM, not the auto ROM thing, which also generates ROMs, but this is for my use case. It just has nicer output in my opinion, and it looks kind of nice. And I need it for my current build, and I have no intention at all to insert binary data into the game manually. I want to have some program which does it for me. So AutoROM is quite cool, but not the design I need. So I wrote my own thing. Probably works similar, I don't know. And yeah, this counter is from someone, I don't know his in-game name, so I cannot credit him properly, but Nicholas something. Synchronous counter can be found in Discord, and that's where I got it. So I just hooked this up so that I can test it. It's currently set that each address line in the ROM prints its address back to the output just by having the proper wires hooked up. Yeah, so that is the result. I can freely define the size in terms of bit width and amounts of addresses. There's a limitation though that you need more bits than address bits possible. That's because the decoder is right on top. I could have less, I could have more bits than addresses, possible addresses. That's totally fine. Like 4-bit addresses and 8-bit data, but not the other way around for the simple reason of the size here. The wires attached directly to the inverter there. So this is the design I had in my mind from the very beginning. And now I'm gonna show you, practically you could stop the video here if you're not interested in how I made it, and the whole story behind that, how I made it. So for starters, this is my playground. This is where I spent my last days, figuring out how to do this. I wrote the whole thing from scratch. I sometimes occasionally asked Jimmy about sizes and components because I needed some numbers. And yeah, I will give you a raw overview. And I try to explain how the format works. The format gets stored as tungboards. You probably know that if you played the game. Each of these is a single file called, with the file ending tungboard. It's a binary file, and if I got that properly, it's just an C# object which is vomited as binary into a file, and then read again. However, that makes it quite difficult to read that file in any other language than C# because there's no library for it. At first I thought, let's read the binary, awesome! And then I looked at it and I was like, let's not read the binary. Okay, so here is board to JSON, credits to Stenodin, cannot pronounce that. Anyway, this dude made this tool. I was not able to use it until I properly installed Mono, which basically is able to execute exe files and a lot of DLL stuff. This converts the saves to JSON and the other way around. It was nice for me to use it as debugging, and I used it to finally create, or eventually create, the tungboard files. Yeah. So I looked at the JSON in the beginning and thought like, okay, cool, you got components like boards, and you can set the color of such a board. That's what I messed with in the beginning. And then you have relation, like the first element in such a file is always a board component. Like you have the X and Z, so that's the width, how big it is. Then you got the color, that's from 0 to 1, RGB, easy. And then you got a position, I don't know what that is good for in the root element, like, who knows? And also rotation for the root pane. To be honest, these values are kind of unnecessary. And can have children. So this is funny. I will try to not comment on this format. Oh, I did already. I said that these are useless. Practically useless. Anyway, yeah, there's a bunch of issues with this, but it works. So basically we got a board, like, you know, are everywhere here. Like, there's plenty buttload of boards, and boards are the base components, so you need to be able to handle boards, else you can drop whatever you're doing. And these can be nested. So I saw, okay, this is simple JSON, you got a type here. Sadly, this type has to be the first element in the JSON. If it's not, it will fail it instead of searching for it. So that's kind of down on the conversion tool, kind of downside. Yeah, and else it's the same thing. You got a position and an angle thing. This is a problem because this is XYZ, and you never know which order they get executed and how whatever. Yeah, okay, I can probably handle that. That's what I thought, and I was wrong. Well, eventually I did handle it. And you can see that you got a board in a board, and on top of that there's an inverter. And inverter also has the same stuff. It has position, and it has some extra option. So this is the base concept of the file. You got components in components in components, so you can always have boards and boards can have other components. I did not implement all components, but whatever. The gist of this is that positions are relative, so this position is relative to the 0 point of the board before. Same here. This position is relative to wherever this board is placed. That is an issue. Well, is it an issue? No, it's not. I started playing with this. I placed some elements like next to it here and like this. I tested a bit, and I dumped a board on top besides, like an XYZ, and I played a bit with it. I tried to figure out how do rotations work, how does it work, how can I rotate stuff, how is it related to each other, and trying to understand it, and I got that, yeah, they are relative to each other, and you have to rotate them in some weird manner, which I didn't understand yet. Here, I was trying to figure out what the size of each board is, but well, it was quicker to ask the people, and that told me that one of these squares is 0.3 meters wide, which is equivalent to 30 centimeters. Awesome metric unit, like it. So yeah, there's a small problem with that. Like I didn't figure this out properly for some reason. I was I don't know, brain dead. Let be that. However, I thought like, okay, awesome, I know everything I need to know. I can just export a component to look at it, know how the JSON looks, and then give it a go. So I started with this. I started with a simple board. That is literally my start after all that crap which I placed over there. So I placed stuff against it, I rotated stuff, I moved it into the bottom, and then I slowly started to figure out how it works. Like, you spawn an element relative to somewhere, and then you move it, and you do some for loops so that you get more of that stuff, and then you expand stuff depending on some other variable. So this is just literally simple code which generates relative objects. I mean, simple objects in code which place the stuff down. So you spawn them, you estimate where they have to be, and then you just adjust the position. Because it's relative, you don't know how to rotate stuff. You just put it down and eventually you get where you want to be. This works awesome. So I was like, hey cool, I can work with this relative stuff. Okay, awesome, epic. Is this still recording? Yes. Okay, so I continued. I said, hey, let's put inserters on top, because I knew how the ROM should look eventually. So I dumped inverters there, inserters, inverters, and I saw, not factorial here, and I saw they're too deep, so I put it on top, and I rotated them, and then I was like, yay, awesome, this looks epic, and here we go, this is easy. I placed some, oh yeah, wait, here I was placing packs. Like, oh damn, I can't see them, so what I do? I put them up. Oh, I need to correct them. Okay, cool. So here, now they're all in place. Perfect. And this is the point where you might want to place wires. And then it all went down. This was one day work. This stuff which I just showed you. And then I had to place wires. That was no. I just no, because wires are relative, and wires are defined as one point and a direction in Euler angles. Let me have a look if I have one here. Probably in the last one. Yeah, that's the safe wire. So we got a position, we got angles, that's totally normal, and we got length. And that's all I knew. I was like, okay, cool. What now? I can connect them, but I cannot do code which does that for me. And should I have the relative positions to everything always? It's madness. And if you don't know which, oh, I should have mentioned that. Like, if you have a board, like for example this board, this corner right here in front. That's the 0 point in the middle of the board. Like, there's the point. And that direction is positive x, that is negative x, that is positive z, and that is negative x. It's as easy as that. It's super easy, as long as you stay in this one board. If you place components on this, it's super easy. But as soon as you place another board there, the coordinate system is slightly different. X is still there, negative x is still there, but z is in the bottom, and negative z is there, and if I go there where it used to be positive z, it now is positive y. And that is because this board is rotated. It has a different coordinate system. Isn't that epic? So the base problem of that is, if I want to, for example, if I have like 3 layers of boards here, that means I 3 times rotated the coordinate system. And I don't know how they modify. And I'm just like, where does the wire now need to be? Do I need to do plus or minus or x or z? And what the heck? I was totally lost. What should I say? Eventually I got a little idea, and that is you can put a little peg here, and for example for each board, and that peg has a 0 location and 0 rotation. That means you can see where the 0 point of a board is, and you see the orientation of it. Like, you can see where the axes are. Obviously there's x, positive x-axis, and there's positive z, because the peg is on the edge, on that edge of the board. Here it has different function, I don't know, it doesn't matter. It's just garbage. This is all garbage and it's gonna be deleted, but I wanted to keep this in a video. So I quickly had a thought. I need a tool, something which is a bit more capable of just melting your brain. You need to build this tool once, which will melt your brain like plenty of times, and I got it working. It's a tool which has one coordinate system, one absolute coordinate system, no rotation, no anything. It just has that coordinate system, one x-axis, one z-axis, one y-axis, and just 6 possible rotations, each of the axes in both directions. That's 6 rotations in the absolute coordinate system. There is no weird thinking. The problem is that needs a framework. Such a framework is kind of a problem. it's really a problem, and most of the garbage you can see here is from creating that framework. You start by putting stuff together and trying to figure out, oh, by the way, up to this point, what you can see here is total mess. That was my second attempt of doing this framework. It looks good, yeah, it looks good. It's absolute coordinates, right? But the rotations are completely random. And the first layer, easy. That ring around is the first layer, but that block, that board there is that's the second layer. You can see there's sometimes here, sometimes there. That's not where it should be. So I tried to place a board somewhere relative to the first layer of boards, and I totally failed the position. Here, that's where it started. I placed the board and I said like, okay, it needs to be some relative of that. Or was this from the third attempt? I don't know. So, yeah, it's horrible. I placed boards and I rotated them. I tried to change the algorithm. I tried to change how it works, and it was just awful. I built these neat towers. Like, every time I had some new model, I had to place that model. And if you place it in the air, like on these towers or trees, you can see what is actually happening. You can see that that model here is also down there, and it's the same stuff, the current model. I need to test a specific situation, so I build a model for that, which perfectly does it, and place it at a random position, which gives these super nice looking artifacts here. I really love them. It looks epic. But yeah, what should I say? I think it's time to bore you with some code. Yes, showing code, production code, which I just finished. Like, there's no cleanup in the code at all. And yeah, okay, I'm just gonna show you the base of it. So I started with this. This is very simple stuff. It's Java, everything. I was like, I tried to keep it, I tried to summarize it. I had like properties for each board. A board as a component. A board can have other components as children. And yeah, and then I said, okay, cool, now I have all the values, I inserted them here, and now I can just print it as JSON. And it asks all the children, hey, give me your JSON, and then it builds a whole JSON tree and stuff like that. So that's pretty straightforward. There's no relative, no anything. That's how I did the first things. Component had a parent, and fancy stuff here. These are some constants I keep using, I constantly use. That's just the distances, like easy to use difference, so that I don't have to remember the numbers. In fact, I had to remember them anyway, because this doesn't help a lot. 1 divided by 2, 3 divided by 4 or something, I don't know. Or 3 times 1 divided by 4, that doesn't really matter, it's just numbers and relations. I got inverter, so that's that, and I got a through blotter, so that's just simple. I know the data, I know how to print the data as JSON classes. Pretty easy. And I try to use them here, and it's what, so this is hell. Well, this is hell. I don't know. Don't mind this. This is old code. This is all old code. All. Close this. And actually I already removed the code which uses the very old TUNG components, because these don't know anything about relations. I got to the point where I tried to place a wire, and here are my horrible attempts of doing so. I don't know. At least I managed to calculate the length, and that was it. Doesn't matter. Begin. That was the very first attempt. It's garbage. So I thought, like, I need to make that absolute one. I had absolute components. Awesome. An absolute component is not that much different from the previous component. Let me close this. We got a position, we got a direction, we got a parent. Easy. We got set position, set direction, set parent. Easy. We got weird stuff, which is the global position. So I thought, make up my mind. What do I want? What do I stuff? And these are like the more important garbage things. These are like utter hell. They are hell. They are literally hell. Don't think about... Okay, I'm gonna show them to you anyway. Oops. So I got the second version, that was this one, the end components, the absolute. I just named it end components because components wasn't used. it's still total development code. It's horrible. I mean, like, you can even see my path to my game here. It's horrible, awful. Anyway, so you put a pack, you set the direction, you can set positions, you can make new components, you insert components into others, and you give them numbers and stuff. You have inverter, which does nothing, it's simple copy. You have a pack, which also does nothing. Oh, by the way, nice attempt for something which I have to implement later, and this was the only good thing which I started. I made a vector class. The vector class has X, Y, Z, it stores them, and it is able to perform mathematical operations. It can flip itself, you can divide it, you can scale it. You can get the length from it, you can normalize it, you can do stuff with it. I mean, it's just a vector class. I simply wrote this together for whatever I needed. I've also had attempts where I assumed I could use the cross product. I ditched them. That's horrible. That's math. Don't use math for anything. It's bad. Okay, actually, math is not bad. I tried to use quaternions. I investigated them. How does it work? I gave them up. I tried to use math. 3D math, like vectors and stuff. I gave it up. Like this stuff. I gave it up. I used simple logic in the end. Because that's the only thing which kind of is intuitive to me. I could use math, I could learn math, but nah. Okay, this is the last thing which is worth mentioning. Same thing, it's still a board. A board has children, a board has a color, a board has a size. A board has a global position and a corrected global position. What is that? What is that? Back to TUNG. I say that the corner of a board is the center of it, which is horrible. If you have the center of the board in the corner, you cannot rotate the board without putting it in a different position. So I said, if I have a board or any component, that fixed point needs to be in the middle of it. If it's not in the middle, I cannot rotate it. That's awful. So I had a global position, which is the middle of a component. So I needed to fix the position to get the actual position of the board. Back to Eclipse. So, yeah. This is failure attempt 2. I said, hey, here's the point. It should be, if the board is never rotated, if the board was never rotated, the position should be this. That is correct term, that's perfectly fine. That is, and I still use that thing. It's the corner of that board if it's never rotated. So I made fixed origin. This has a fixed point. Oh, this is actually a method which I never finished. That was one of my attempts to do math. After I realized that I cannot use the normal fixed origin, which is simple case if the current coordinate system is the default one. Then if I then want this, like positive y coordinate system, I need to do following modifications to it. However, if you're not as dumb as I used to be, you may notice a coordinate system has 3 axes which can each be in 2 directions. That makes 3 by 6, that's 18 possibilities of a coordinate system, am I right? Wait, no. Each positive pointing axis can be in 6 directions. That means all the others can be in 5 directions, and then the last axis can be in 4 directions. 6 by 5 by 4, where's my calculator? I'm too stupid for that. That's 6 by 20, right? 6 by 5 by 4? 120. I'm right, 6 by 20. 120 possibilities to put a coordinate system, and this is one. This is one way to rotate the default coordinate system to something else. Genius as I am, I attempted to use this method for the other permutations of a coordinate system. That doesn't work. It cannot work. It's not possible. Equals stupid. Let's take a vector, a direction vector, which just points in one of 6 possibilities. Get me? 1 of 6. Totally wrong. And then figure out what the Euler angles for that is. That's totally stupid. I was so retarded. This works. This works perfectly if you just have one layer. The baseboard and one board layer on top. Then it works. You can perfectly work with that. Don't start the second layer. It doesn't work. I failed it. I learned it the hard way. It's horrible. Okay, begun. I'm not gonna show you this anymore. I worked with it. I did some stuff with it. I don't know which of the attempts are from the second or third, like, of the things here. Is my fly mode on or off? Oh, now it's off. Why am I falling down? Oh, it's because I'm looking downward. Was like, no, this doesn't work. I started stuff. I think I made even these things here. And that was the next step. I tried to understand what happens. What is even possible? What is going wrong? And then I was like, no, this can't work. This can't work, as I just showed you. I thought, like, I need something. And then I went to bed. In the middle of the day, I went to bed, lay down, closed my eyes, put on a sleeping mask, had music on, doesn't matter. Turn off all the gigabytes of visual data which my brain absorbs and just had a black canvas to think with. I was laying in bed, not doing anything. I saw coordinate system. I saw an axis, a vector, pointing to the next coordinate system, which had a different angle, and pointing something to the next coordinate system. I saw it in my eyes. I had like GPU power to do simple line drawing in my brain with the brain power. It's awesome. However, this got me the idea. I need to have a modificator which modificates my current coordinate system, a random point in it, to the original coordinate system. Or the other way around. Doesn't matter. I need this conversion thing. So I did it. I made the conversion thing. I don't know if this was day 2 or 3 already since I've been working on this. It's horrible. It's the magic converter. It's magic. I still have my exportable thing. That's just an interface for as JSON. Doesn't really matter. I thought like, hey cool, let's have a color thing. I saw, what is the default color? Oh, it's actually this one. Oh yeah, with some rounding errors, but it's practically exactly this color. That's the board color. So I said, cool, let's make a color object with the default color. That is. Cool. I don't need colors for the final product, so I didn't even use this properly. I just generate this class like in each of the objects and then leave it somewhere. I thought like, okay, I need directions. 6 of them. I need 6 directions. 6 directions, that's good. So I got for each axis 2 of them. I got a vector for that and I just stored if it's positive and negative for ease of use. And I have a string here for printing in console, which is currently quite corrupted. However, that is just a simple enum, which lets me convert a vector to a direction and a direction to a vector. Awesome. Also, I had the issue, what if a user is stupid enough to use a direction which is not one of these? I don't want to catch that, so if I'm using this enum, the user cannot do that. And the thing is, if I make this a proper framework, which will be the case, I will only be using these 6 directions. That means no matter which, what you do, you cannot do anything but aligned components. The simple reason for that is, I never need anything which is not aligned, for starters, and second is I'm not using math, I'm using logic to do all the conversion. That means I need to have these grid things because else I cannot use my previous fixed origin method, the one which was on charge of rotation. That one already, it just swaps around x and y values and in the best case negates them. That's the whole method does. That's not even math, it's just kicking x's around. And that only works if I have these 6 directions and no more. That's it. So that's why I made this enum and said, I need it. Final. And then I made components. I started with the board. I said the board is the most important component. I need the board itself creates a new coordinate system. It's the most important thing. And whatever I do after that doesn't matter. The boards have to work with any layer. Everything else is not important. So I made a board. I said, cool. Board has the same properties as before. Board can have children, blah blah, whatever. And this is the difference. All the math, or let's say not math, logic disappeared. I dumped it in the magic converter. It's not here anymore. It's gone. That's a good thing. All the bad things are in the magic converter because it does magic things which nobody needs to understand. It's gone. It's out of the way. I tried to put it in the JSON one. I had a resolve before. I tried to put it there. I dumped the resolve. And now I got it back and dumped it in the magic converter. Awesome. I don't need to do anything. Look how clean this is. That's how I define a board. I just say, here is the stupid starting point. I just need to put this because of the size of the board. And then I say, give me a new coordinate system. Happy. Nice. And then I give that new coordinate system in the magic converter to my children. Have fun with my coordinate system instead of the one which my parent used to have. So the next thing I did was the magic converter. It's magic, you know. By the time I switched to several different types of run stuff, like I always have some create ROM method and did a lot of tests here in the main stuff. I have this one which I showed you earlier. That's just a bunch of boards where I stick random components just for testing. That's all the components you can see in the world. It's just that stuff. And I got a bunch of create ROMs and stuff. I just did this file and started a new one because this one got messy. I just took this one with me, the export board, which basically just execute the board to JSON and converts the JSON object to whatever text, to JSON string. That doesn't matter. What we do here is we create a ROM. That is, we start with a board, base board, and we finish that by calling resolve with the new magic converter, and then we export the base. If we don't call this, the program will complain. So we export the base. That is the same code as before. No need to show that. It's just calling that. It's just Java stuff. It doesn't really matter. The thing which is actually important is the magic converter. So let's take a peek. I'll make it smaller so you can see what was actually in here. We got a parent magic converter. It's quite important. Not. I think I never used it. I don't know. I got this, which is just a debugging option, an ID for the magic converter to see which level it was. I used this because I had a bug. I got rid of it. And then I got this. I thought like each current system, that's what I told you earlier, has 6 axes and they can point in whatever 3 axes and they can point in 6 directions each. However, it will never be the case that 2 of them point in the same direction or in the opposite direction. That's never the case. But that is convention. So I made this and I said, okay, cool. I just need to know what the 3 axes of my coordinate system point at in the absolute system. If I know that, I can, in theory, simply swap the components of it. And this is a pattern, a programming pattern, which I really love. I'm using tunnels. What is a tunnel? Well, a tunnel is a thing which has a value. You can put the value in, you can take the value out. That's all you can do. Like, you just put something in and get it back. That's it. And the pause tunnel, which I'm using here, does nothing. And the negative tunnel, that is a tricky one. It negates whatever you insert there, and when you get it out, it is negated. So this one negates it, and this one doesn't. What does that give me? What do I need that for? Well, it's quite simple. Let me show you. This is the magic one. This is where we create the tunnels. I go here and say, okay, let's look at the axis of the x. What is the x-axis pointing to? Is it positive or negative? If it's positive, I give it a positive tunnel. If it's negative, I give it a negative tunnel. What is it good for? I go back to the other one. Keep in mind, I said we have 6 directions, 6 possible. directions, and all we do is we invert the components in here and swap them around. So epsilon gets, for example, swapped with x, and x gets inverted. So that's all the tool set I need. That's what I did here, just in flexible. I said, if I know where this coordinate system lies, I can create this flexible thing with tunnels. And the good thing about tunnels is, that's almost zero performance. I could, in theory, just dump hundreds of data in there for no reason, but whatever. It doesn't really matter. Each board has one of these things, and each component will use these tunnels because they need to convert their absolute position to some relative position. So I took the tunnels and I said, okay, cool. So first you need to know if it's a negative positive tunnel, because I need to know if I need to invert it. So if it's a positive axis, which points to a positive axis, no need to convert that because positive stays positive. But if a positive axis points to a negative axis, I need to invert it. However, a negative axis points to a negative axis, I don't. But I'm not checking for negative axes here, I'm checking for the positive ones. The next thing I do is I check which axis actually is, X, Y, or Z, and create the tunnel. And I link the tunnel. The inputs and the outputs needs to be linked, so I link them. If I know that X and epsilon needs to be swapped, I connect X and epsilon with X. If that makes sense to you. However, these tunnels are set up. After I know these faces, I can set up the tunnels. Cool. What are the tunnels good for? What else do I need? I need a global position. This is quite important. I need to know where in my absolute position space is my current coordinate system 0 point relative to the global coordinate system, the one of the baseboard. Did I ever use that? Yeah, I did. Doesn't matter. That's for later. So I got the tunnels, and that's the actual key points here. These ones. After I got the tunnels, I can use this stuff here. So what is it? Let me show you. I said I need to convert the absolute positions to relative positions. So how do I do that? I insert directions, for example. Well, let's start with the convert ones. The convert ones are the actual relevant ones. I put in a vector, which is basically an absolute position. I subtract the global position of that vector, so I get the relative position of that vector which I inserted to the 0 point in the current coordinate system. And all I need to do now is rotate that point to the right, wherever, right, you know, the coordinate system has like 6 halves, and so that's 8 subsections, and I need to rotate the point in the right subsection. And that's something I can do by just using the tunnels. I don't need to apply math here because I already did the math for the tunnels. I pre-compiled the math or something like that. And because I only have 6 directions, which are aligned with the axis, with the normal axis, that means I can just use these tunnels to convert the number. And then I just return the number. And that's it. That's as easy as it seems to convert a point. I did the same for directions, except that I just get the vector for the direction, I dump in the vector into the rotation thing, the tunnels, and I get the vector back, and I turn that vector back to the direction and return the direction. That's how you rotate that one. There's 2 special cases here, and that is rotate local direction and rotate absolute position. These don't have any subtract and addition stuff here, because they just need to rotate. That's their base purpose. So in this case, I give it an absolute position, say, wherever that is, don't care, just rotate it for me, okay? There are some use cases for it. I'll get to them later. So I basically am using the tunnels here and rotate that. This one is special, rotate local direction. You put in a local direction in the output and get it out of the input. Why is this? I had a bunch of bugs where I had like in and out, and it was so, why is there still one of them? Except, I'm not using this method. So that explains why this is not, why I did not notice that one yet. Here it is. This is rotate local position. You put in the output and you get it out of the input. That's how it should work. If you put something in the output and you take it out of the output or with the input, there is no conversion at all, and that is bad. I did that a bunch of times. Dude, you don't want to know how many bugs I had in this. It's horrible. Okay. Let me continue. So these are the tools which I have in the coordinate system. The tunnels are how I use them. Like how I use the tools, how I make them possible. So that's not really magic. I mean, like, yes, the tunnels are a bit of magic, but the main magic is actually how do these things get created or figured out, and that is what happens in the spawn one. Oh, by the way, this is something which should begin. So this is the spawn thing. Oh, that looks short, right? Isn't it short? Short means easy, doesn't it? Cool. Okay, short notice. That's also one of my bugs. The spawn method is executed in the parent of the class which I want to create. So whenever I run, for example, convert absolute direction, that is in the parent coordinate system. I start with the XYZ. I said like, okay, what do I need? I want to have new board. So here in board, I say, spawn me new coordinate system. Here you got stuff, you got my absolute position, you got my facing, and you got where my fixed point is. So that is what this thing gets. Begin. So there we go, and we say, okay, give me that global direction, like the direction, the global system where this board has to face to. Give my parent and ask my parent, which direction is that in your coordinate system, because I need to place my rotation in your coordinate system. And then I get a local face. This if else was 6 cases. 6 awesome cases for each of the axes or directions. That's stupid, because why would I need to put 6 if the user doesn't care if the board is upside or downside? It just need to have the right direction. It doesn't matter. It has a position. It can be 100 or 180 degrees. Who cares? It took me a while to realize that. However, I came up with, it doesn't matter. I just need to filter for axes, and I just use one. For 2 axes, I need 1 board rotation. That makes things a lot easier. Trust me. It doesn't really matter if you don't have 3. If you just have 3 of 6 possible board rotations in the whole thing, nobody cares. So, what have I done here? I said, give me the fixed point and rotate it accordingly to that target position. That is rotation here, but I just used my common math, which is swap the axes and negate him in some cases, and that's it. So yeah, that's how I get the rotated fixed point. The rotated fixed point is following. If you are in the parent, in the global, no, if you are in the parent coordinate system, and you take the fixed point and you add it on top of, add it on top of the parent position, the local position of that this new coordinate target position, you get the fixed point. So what I did here is I said, okay, parent, I got the local rotation, because the local rotation is super easy to create. I just need to run this 3 times and I got local things. So here, parent, take the local one and give me the absolute one. So that was the one which I showed you here. You give it the local one, it gives you the absolute, and then you got the absolute fixed point. So what do? You take the global position of that board, you add the absolute to get the real global position. The real one is important because the real one is what you work with. The real one gets exported, not my pseudo position, which is in the middle of the board. So I got the global position, and I did some weird stuff here, which is probably very bullshit, isn't it? No, it's not. Anyway, since my thing obviously works, this must be correct. If parent is not 0, it doesn't really matter if But right, it's if I'm not the first board, if I'm the very first board, I don't need to do this. Never mind that case. Anyway, what I do is I take the global position and I convert it to the local position. Means the location of this coordinate system in the parent port, in the parent's coordinate system. I skipped some things, and that is the XYZ. I said that's the magic thing, how to generate them. And be careful, I tricked. I did it so easy. What I did was, if I am if I pretend I'm the baseboard with the perfect coordinate system, and I have this following rotation or this, then these are my 3 axes which I need to have. Okay, so far? No, I'm the second iteration, the second board. The rotation is totally different. I'm complete different coordinate system. It doesn't work anymore. The axes are wrong. So what do? I say, hey, parent, here go the absolute rotation. Give me whatever your rotation for that is. Good luck. So I just pretend I have the best board, the base board with a good coordinate system. I say that's the axis which I would have after this rotation. So parent, give me whatever that is for you, and then just store that as my new axis. Isn't that epic? It's magic. That's not math. That's logic. It just works. I don't need to understand it. It works. Whatever. And there also are Euler rotations, because if the board is in the base, if the board is in the base coordinate system and in the major coordinate system, that's the rotations which I have to perform. These do not change because they are equal for each board. That's what I tried to do here, and I really had some issues where I tried to, do I need to rotate it more than once? Do I need to convert that? It's all, no, I don't need to. It's all cool. So that's all the information which I generate here when I want to create a new coordinate system. Epic. Epic. So that's when I say, hey cool, give me a new magic converter. That's the stuff you need to take. You need to know. Please, there, welcome. Set up tunnels and be quiet. Magic converter, just some random stuff. Set up tunnel, that's the first one. The overparent, whatever, that just gives some stuff. We did. We have a new coordinate system. That was tough work. Took me ages to do that. Ages. I'm still literally, I aged 3 years here in this last 5 days, so 4 days, whatever. I started Monday. And it's Saturday? It's Friday, let it be Friday. No, wait, here, we got, where's my, yeah, Saturday. Anyway. So what I do here is, okay, cool, here, magic converter, give me my local position of the board, you know it, you calculated it, give me as JSON, and give me the rotation I need to know. Cool, I got the board. Done. That's how you do the board magic, that's how you do the coordinate system. Back to TUNG. That's how you can do this stuff. I had to start all over again. I said, hey cool, I need to start all over, so this time I do the same as over there, but with absolute positions. And then I started to add packs. Packs? There's nothing difficult about them. Yeah, they do have a magic converter over their parent, but yeah, they have a facing. Yeah, the facing gets converted with this if else. Easy. The position gets converted at that point. Easy. Nothing to fear there. It works perfectly, as you can see. Here, there the packs are. I keep turning off fly mode. So then I started and said like, hey, I need oh wait, where did I continue? Can you stop flying? I don't know where it stopped, but yeah, it's big, it's messy, it's stuff. Anyway, I started to put components and I was like, okay, cool, yeah, inverters, cool, inverters, nice, inverters, epic, cool, they work, working is awesome. The problem with inverters is they have 2 axes. So they have the one for the input and for the output. Let's have a look. Easy. I have 2 facings. and I got rotate input direction, rotate output direction, and I got this. That's each combination of these two, 24 at that. You can see them over here. I was tempted to like find some neat math to fix this problem, but then I thought like, okay, nice, it's 24 possibilities. I'm quite tired. I can do it this way. I just put all the combinations in one line and then I fix them until all of them are correct for the base coordinate system, and everything else gets done by the magic converter. I don't need to do anything. I just define this once for every 24 case and then I'm done with it. Works. Cool. So that is the inverter. Inverter done. So that's the point where we need wires, right? That's where I started here. Right, I continued here. Here was where I continued. I got to the point where I put these packs, and then I started with the smaller thing where I placed the inverters. I moved them a bit around, and then I placed the packs on it. And at the end of here, I was able to place wires. Wires. Did I mention that wires had been very horrible over here? They had been the same level of horribility in absolute system, except that I could be sure the position was right. So what I had to do was like, I'm like, okay, I need to put this down and export it and see what is this even, and I figured out some facts. The center point or the location of a wire is in the middle of it. It has to be. The length is that's the length. There's nothing wrong with it. But the point is, you need to put it in the middle, and then you need to rotate it correctly. So you cannot just say it's in this pack and the rotation defines where it ends up. No, you have to say it's in the middle of the wire, wherever that may be. Well, it's easy to calculate that position. I could have done that, yes, but that means the rotation needs to match the location. I was not able to figure out some rotations to get this kind of working, and that was the point where I started asking Jimmy about, hey, is Unity using this weird, we rotate by Z first, then X first, and then second, and then Y? And yes, it was. I asked, and it worked. I did some rotations with the inverters, as you can see, and yeah, that's how it works. X, Y, Z rotations. Positive, all of them. Oh, that's probably where I first started the inverters, and then I moved it over there because there's more space. Okay, time to show you wires. Wires are hate. That's not love, that's just hate. Wires need math. They do. But the math they need are not some quaternions, not some 3D shit. Oh no, I said a swear word. I'm so sorry. Not some 3D stuff. So it's just simple trigonometry. That's something I can work with. That's something I totally understand. That's easy. Trigonometry, I love it. I really can work with trigonometry. Epic. So I came up with some stuff. Yes, I did not really. I tried to figure out how to get. I googled a bit of stuff, and then I found conversion to pitch and yaw. Actually, I should be able to just with 2 angles define a wire. And I was able to. This is how I did it. Bug 1. I did not use the rotated direction, I used the absolute direction to rotate a wire. Works perfectly well if you're in a default coordinate system which points with Y to the top. In all other coordinate system it doesn't work. So I forgot this, I got a bunch of errors, it took me a bunch of time. That was one. So what did I do here to figure out the wire rotation? That's quite easy. I said, hey, give me the arcus sinus and give me the hypotenuses, the lengths of the wire, and the Y difference of how high the wire is from the center of it. I knew that the default wire direction is this one. It's in the positive Z direction. That means no Y level at all. Y should be 0. So if this is 0, then there is no y rotation. No change in y. I divide that by length. Length shall not be 0. If that is the case, someone messed up the positions. And then I get the sinus. Converted to degrees because the file needs degrees. And to invert that because of the direction. However, there is the x rotation. Remember, x is before y. So I rotate around x first. That is, in inverter speaking, it is the angle of how far it looks up or down. That is the x rotation. If I have not applied any y rotation, the x rotation is the one which defines how the wire goes up or down from its default position. This is default, it goes up or down. So that is totally fine. Next thing I do is I say, okay, I got y, I can dump y. What I need now is x and z, and I get the length of that. And this would be good with a graph, but I'm too lazy to make a photograph of my sketchbook and insert it into the video. So what I do here is I check if it's the length of 0. If it's 0, there is no rotation for reasons, whatever. Let's just ignore that case. So what I do is I get that thing. What is the set? That is the distance from the 0 point to the outer point position of the hypotenuse of a triangle. If I want to take the x distance and do the same, I want to get the angle. So what I get here is the rotation of y. What I can do here is I can rotate the wire into the position I need. So basically, depending on how far the z-axis is, no, the x-axis is used here, so how far the wire goes left or right, I can know how far I need to rotate it. It doesn't matter how high it goes in y level, because it's just depending on how far left and right it is, and I divide that by the length it has to get the actual angle. Use some trigonometric knowledge and then you figure it out. However, this only works for positive set values, which gave me a bug later on, or actually I ran into this bug first and this one later. But to fix this bug, I knew the solution for that bug, I just did not apply it. So I fixed that bug and then I ran to that bug and say, oh, I know the solution because I figured it out already, and just recommented that in. If this considers the y-axis, this considers the x-axis, but the z-axis doesn't get considered. It's not that important. But if it's negative, that means this is on the other side. And I said that a coordinate system has 8 sections, a 3D one. And the one opposite to each other are where the line crosses through. The center point of the line is in the middle of the coordinate system. So if I am in one sector of that 8 in the coordinate system, I am in the opposite, the wire is also in the opposite direction. It doesn't matter which one I define. So what I do is, when it's behind Z, I just invert both of the angles, because then I am the opposite one. That is totally fine, because then I have all 8 perfectly defined. All 8 directions the wire can have, or it's actually 4. And that's how I get the direction and oil angles. Bam! It took me some time, but once I got that done, I was like, whew, oh, I got this going, it's almost finished. Awesome. There's also plotters. Plotters are not really that interesting. I just had a local direction, local facing again. I checked which it was, and I just said which Euler rotation it is to get that one. I did it like with the inverters. I was like lazy, and I just said, hey, I need plotters, so I just put them down here, and then I rotate them until they fit. And then you get something like this, because the center point of the plotter was, well, I don't know. So just say the center point of the plotter has to be in the middle, because that's where I want it to be. Because then it's very easy to rotate it in whatever position I want to. And so I just applied some locational fix in the local positioning, which is this position fix. I just applied it, it's just half square movements, quite easy. And then apply that later on when I convert to the position, and what I get is a neat row, perfectly aligned blotters, perfect. At this point in time I got wires ready. I got wires on the bottom. I got wires on top of here, and these are all in the normal coordinate system, that's why they worked. And then I got stuck on, at the point where I had to connect that one with the one down there. I placed pegs like here and there to confirm that the position which I calculated are correct. I really was kind of annoyed because like these wires work perfectly but not that one. Well, that was the first of the bugs where I forgot to put it in the absolute coordinate system, in the relative local coordinate system. Whatever, eventually I got that one done. I showed you how the bugs worked, and well, that's some attempts of how I tried to get it working. It's the same thing over and over. I tried to edit the JSON to figure out what I did wrong. Where did I go wrong? It was a huge pain. Okay, damn, I'm over an hour recording. It took way too long than it should be. I built all that stuff together and I was like, okay, cool, now I can start, put the decoder on top. The decoder is nothing special, it's just a bunch of blotters. Through blotters. I don't know how I rotated these, but that was much more easy. I also had some neat little adjustment to them. Like I just said, hey, cool, I got a direction and I know that the center point needs to be moved by a bit, so I just scale the facing vector and add it onto the position. Fix, done, cool. So just had to convert the position and the facing later on and was done with it. Is there something interesting here? Default pack. No, that's just the default pack. And the plotter, which has that, I showed that. So I showed you all components, and that is the point. We got the stuff working, and so I got this point done. All the wires. Like these two here are the ones for the decoding. I had an issue that only that one or the top one worked. That was because it didn't consider the local and absolute rotation, so that means one of them was wrong because they are in the opposite coordinate system, 180 degrees rotated, so one angle was always negative when it shouldn't be, and the other way around. Until I fixed that relative thing, and then it worked perfectly fine. And then there we go. So I thought like, okay, cool, now I got that working, I need to get the blotter and the inverter on top. So I made this little bridge, whatever that was the case already. So I put these here, and that was the point where I was like, hey, cool, I put a wire here and it's not appearing. Awesome, I got the stupid wire again. That was my second bug, which I found in the wire thing. And once that was done, I had to fix the orientation of the blotter, and I got that working, and eventually the blotter was properly positioned, and then it looked like this. And I was like, cool, I can just define the wire positions and it's working. Epic. Epic. So the next point was, I need to remove some wires to get the address decoder done. And that was the last thing I did. And once that was done, I got this neat little unit here. And then all I did was I put in some data. I can show you that in code. And yeah, then I was almost at the end of it. Like, that's how it worked. And I will only briefly show you how that generation works, because it's like a real mess right now. It's horrible. Basically, there's shell set bit, you give it a bit, an address, and what it does, it just gives you the address back. So it says like, okay, you're checking this first bit, and that's in the third address, so we take 3 and check if the bit 3, or yeah, bit 3 is set in there. Or whatever. However, this gives you exactly the address back for the exact bit which you are. That's the data for one cell. Eventually I need to replace this with some array or whatever. Some binary input source for whatever I want to insert there. So this is where I create the ROM. I have a bit width and I have word amount. I create a base thing. And I have a lot of vectors and helper variables which do a lot of math. As you can see, I'm using these values everywhere. And then looping over the bits, putting some board as holder there, putting a holder on top of the board. And you always need to supply facing, position. If it's not default, then you need to subtract and add vertices as necessary. Make copies of them, modify some, don't others, and then you iterate over the words, looped in there. Where you create packs, and then you need wires, and you just supply some vertices, or directly generate the vertices. It's a huge mess. And place a random inverters. Well, there's only 2 of them. But anyway, that's how it works. You create, then that was where I created the holder of the baseboard. That was of the decoder board. That's this one here at the side. And then I put the top pane. That's the big one on top. There, and create the decoder. Here it was like I had double the amount of bits because I need to do for each bit. I need to do 2 of these. I need to place 2 of the blotters. So I had like is not negated boolean which flips after each for loop, so that I get in different sections where I place the inverter or the blotter for the beginning part. That is these 2 here. I place the wires which connect these 2, and then a wire which connects to the actual decoder, and then I got the through blotter here, and I put the wire on top of that. And it's just a bunch of math and creation. There's nothing real special about it. Maybe this is interesting. This is basically the wire which connects the blotters to the inverter. So to make the decoder. So this is the whole decoder definition. You got the is not negated, and you're comparing 2 booleans here. So you check if a certain bit is set or not, and that is the bit in the address, which basically is defined by, we take bit half because we're iterating over double the length of bits, so we need to divide that by 2. We got 2 blotters, 2 iterations for 1 bit. And then I invert the order. That is what this bits minus that and minus 1 does. That's the order inversion, because I want to have it on the other side. Then I select the bit by bit shifting. And then I add that on the board and check if it's not 0. That's how I check if the bit is set. The certain bit of the current position in the address. And then I just check, am I in the section which needs the bit set, or in the section which needs the bit unset. That's basically everything it needs to know, because every other one is the inverted one. Like as you can see here, that these are always connected and one is inverted, one not. That's basic ABC of decoders. Nothing to say about that, not much. So that's the basic code which generates it. I would have reached, or I think I have reached the end of the video. I'm gonna, there's a bunch of stuff in code which I need to change. For example, it would be cool if I just supply components and inputs or outputs of the component, and just say, hey, framework, connect these for me, so that I don't need to think about the positions. That would be super cool. I would have a first resolve and a second resolve, so that I can do the components first and then the wires, and that I 100% know where the wires are positioned. Or the components which I need for the wires. And a lot of just other fancy stuff, so that it just becomes more easy to use the framework. And I want to make it open source, but not in the current state. I really need to clean it up. This video might be interesting for TUNG players, which just want to know how the board stuff is working, or the safe format. And for anyone who wants to use my framework eventually, or ever wanted to use something like that, and some who are just sadistic enough to watch my pain of how I actually experienced that stuff, or how I developed it. If you really watched the whole thing, you have to contact me and tell you, hey, I watched it, and then I will be proud of you. I don't care if you like it or dislike it, would be cool. But leaving a comment or contact me is always awesome. Asking questions is always fine. Please do that. And yeah, that's basically everything. I finished this project somehow, and I just had to tell it to you. Okay, so thanks for watching again. Bye.